a virus that is going to infect turkeys. So the ones that we are most concerned about are all belonging to serotype 1, whether it's a standard, very virulent variant, or a reassorted virus. So how did scientists begin to understand that there was not only one type of virus, but multiple different types of viruses? Back in the 1980s, a consortium of researchers, but particularly Dr. Jack Rosenberger and others, started doing experiments with field viruses. They would vaccinate birds with the vaccines that were available at the time, which were only standard viruses. They would vaccinate them and then challenge them with standard viruses. And those birds would actually, obviously, would be protected. But then they took these new viruses that were being isolated from problem farms. They vaccinated the birds with standard viruses, challenged those same vaccinated birds with some of the newer viruses, and they saw that the protection was not as good as what they were seeing before with the standard vaccines. And that's how originally variant A, D, G, and E were found in the United States. And today we know we're all very familiar with Delta or E variant viruses from North America that have been able to spread to many parts of the world. Part of the way that scientists could determine how widespread these variant viruses were, because at the beginning we didn't know, is this an incidental finding, or is this pretty much confined to a geographical area, or is it affecting different countries, or different areas, or the entire United States, or whatever other region? So Dr. Dave Snyder at the University of Maryland devised a system where he developed monoclonal antibodies against different epitopes of IBD. And by using this method, he was able to classify some of the original variant viruses in North America that included GLS, or variant E, Delaware E, or Delaware A, which were very different from some of the standard classic vaccines that were being used at the moment. So we started to understand a little bit better. He worked with hundreds of samples and determined that by using that method, he determined that in essence, most of the viruses that circulated that were already in circulation in the 1980s and 90s were actually variant viruses and not standard viruses. Dr. Snyder also did a lot of work with international samples, and he basically used these monoclonal antibodies to determine what were the general characteristics of American strains and international strains, and was able to determine at the time, many years ago, that most of the variant strains were circulating in North America, but not in other parts of the world, for the most part. But this situation changed, as we know, years after that. Basically, in the larva, with almost 900 samples, they were able to demonstrate that the vast majority of the isolates, where this doesn't have a battery anymore, that the vast majority of the isolates were composed of variant strains. Doesn't have a battery, please. Were composed of variant strains of GLS or Delaware, and there are some regions, geographical regions, where we could still find a lot of viruses. Then we start using molecular techniques, specifically RT-PCR combined with RFLP. And I'll explain what that is. This was done by Dr. Daryl Jackwood, which some of you might be familiar. He is a person that has dedicated his entire life to study infectious personal disease virus. Basically, he was the first one to use molecular methods to try to understand why and what kind of differences you could find between this group of viruses or that group of viruses. So the way this system works is that you have essentially two restriction enzymes. Restriction enzymes specifically cut any specific sequences. For example, I have here nucleotides that are CCATGG. This particular restriction enzyme is going to cut only when it finds this combination of nucleotides. And the other one will cut specifically where it finds that specific sequence of nucleotides. So when you PCR amplify just the hypervariable region of VB2, and then you cut it with its enzymes, then you get different fragments of different sizes. And based on the size of those fragments, you can determine whether a virus belongs to group 1, 2, 3, 4, 5, 6. So for years, industry used this system to classify viruses obtained from the field. What virus is circulating in your farm? Well, I have group 4. Well, you have big problems. You have group 4. We no longer use that classification. But it's important to mention it because for many years, we used to know exactly to which of these groups each one of the different vaccines belonged. Not necessarily, it didn't necessarily mean that one was better than the other. It was just a helpful tool for us to understand a little bit more about the epidemiology of IBD in the field. Then we got a little bit more sophisticated. It's not enough to look for cut sites using enzymes. Let's just sequence the hypervariable region of VB2. What is hypervariable region? It's a genetic region that tends to change a lot more. It's a genetic region that tends to mutate a lot more and therefore generate variants or changes in the field. So, again, Dr. Jackwood's group decided that he was going to take hundreds of viruses and sequence the hypervariable region of VB2 to try to come up with a classification system that would be more precise and that would help us while working in the field to understand the field situation better. So he published this work in around 2017 that is based on sequencing of VB2, specifically. I don't know what's wrong with this. Sometimes technology is not exactly what we want. Okay, so by sequencing the hypervariable region of VB2, only VB2, segment A, he came up with a system that was fairly useful for a few years before it changed again. And basically, all viruses classified within genogroup 1, these are the standard viruses that you know of. Vaccine strains, standard strains, reference strains from the European Union, from North America, South America, and other parts of the world. Genogroup 2 involves the variant viruses from North America. Here you have variants A, E, GLS, AL1, AL2, etc. Then you have genogroup 3, which are essentially the very virulent viruses that were first identified. The ones that were causing a lot of problems in the European Union, Africa, Central Asia, Southeast Asia. Then we have genogroup 4, which is very particular to the Middle East and selected countries of South America, specifically South Brazil, Uruguay, and Northern Argentina. Why? Don't ask me because I cannot explain that, but these are viruses that make their way all the way to South America. Then we have genogroup 5, which is a group that is exclusive to Mexico. And it's a sort of a molecular combination between North American viruses and Latin American viruses, but it's a distinct group. Then we have genogroup 6, which is essentially viruses from the Middle East, Italy, Poland. These happen to be virulent viruses as well. You seem to have a lot of different collection of viruses in the Middle East. And then finally, genogroup 7, which is, or used to be exclusive to Australasia, basically Australia, that had a distinct group. So when we use the system, it's very useful because immunologically, we can determine whether a virus that was isolated in the Congo or in Indonesia, if it really matches any of these groups. So it can be very helpful for epidemiological studies. However, it's incomplete. It's incomplete because it doesn't tell us what's happening with segment B, and it doesn't tell us whether there is a recombination or a reassortment or an exchange of genes. Based on that system, what I did here is I created this phylogenetic tree, basically using sequences from commercial vaccines. And it really, what this phylogenetic tree tells us is that the vast majority of commercial vaccines are classified still within group 1, according to the previous description. A few of them are from group 2, meaning the North American variants. And then an even smaller group is represented by group 7, which is the Australian viruses. Now here, some of you, the ones that like to think a lot and start asking a lot of questions mentally, are starting to ask, well, but I don't have those viruses. Why would I use this one? Why would I use that one? Maybe I'm throwing my money away. No, you're not throwing your money away. It is true that the best protection is achieved when you have exactly the same virus matching what you have circulating in the field, but it doesn't mean that if you use vaccines from any of these groups that you're not going to have any protection. You will have at least some level of protection, and if that is what you have available, that is what you have to use in the field. Then we come up with the most recent classification system that sequences both segment A and segment B. The usefulness of this system is that it has enabled us to be able to determine whether there has been an exchange of genetic material between this virus and this other virus. So maybe this virus contains segment A from the original parental strain, but then somehow it acquired segment B from another circulating virus or from a vaccine virus. So now we know that we have reassortments. A reassortant virus is a virus that has acquired genes from another virus, another IBD strain, that it has been co-circulating in the field. So, based on segments A and B, now we know that there's a lot of different reassortments. And today, you're probably worried about some of the most recent reassortant viruses found in Egypt, but I can assure you, without a doubt, that next year, and in 3 years, and in 5 years, you probably will have other reassortant viruses. The more we look, the more we're going to find different reassortant viruses. So the original work that was done to understand reassortment and classification based on sequencing of both segments A and B, we can see that all of them belong to serotype 1, the ones that are pathogenic for chickens. And the original work identified 8 genogroups. Now we have at least 9, perhaps more, identified for segment A, and at least 5 genogroups for segment B. So you can have, if you do the math, 8 or say 9 times 5, we can find at least 45 different combinations. But now we have more than 9 and more than 5. So for a virus that is RNA, relatively unstable, very able to undergo reassortment or gene exchange, just like any influenza viruses do, it is very likely that we will continue to find reassortant viruses in the field. Now, the good news, the not so bad news, is that the number of cases of acute, very virulent infectious personal disease virus in the field seem to be diminishing. And the ones from reassortant viruses are increasing epidemiologically. Reassortant viruses can be pathogenic, but they're not usually as pathogenic as IBD. So, in a way, it's not a terrible situation from the point of view that, yes, we have reassortants now circulating, but the good news is that they don't tend to be as pathogenic as IBD, like the ones that were identified in the 1980s and 90s. And of course, the more work that is done to identify new reassortant viruses that were not originally classified into that system, have been done in different countries. Portugal, for example, several countries in the Near East, in the Persian Gulf, Poland, other places. So here's the concept of reassortment. We have two viruses, both of them are IBD. This one has a particular segment A and segment B. The same flock happens to be infected also with another virus or with a vaccine virus that is slightly different from the first virus. There is a possibility that one of these viruses or that these viruses will exchange segments, and we end up with a progeny virus that has segment A from the original virus and segment B from the new virus. So that is what we call a reassortment virus. The end result could be a more virulent virus, a virus that is non-viable, that does not survive, or a virus that is going to be able to survive in the population or the geographic region, but causing less disease than the original viruses that were found. In North America, we don't have much evidence of reassortment viruses in broiler chickens. If we go today and take 10,000 samples, almost all of them are going to be variant viruses that are non-reassortant and that don't have very significant mutations. But that is applicable for the broiler industry. The commercial layer industry seems to have reassortant viruses circulating for whatever reason, and probably this is the result of the layer industry using for many more years than the broilers many more vaccines. As I said yesterday, commercial layers used to be vaccinated up to 5 or 6 times, so there's a lot of opportunity of potential reassortment of viruses between vaccine viruses and field viruses. That is one of the reasons why it has been speculated that the more recombinant vaccine you use and the less live attenuated vaccine you use, you need both. But the more recombinants you use and the less live attenuated vaccine you use, the less are going to be your chances for reassortment in the future. Here's an example of the many reassortant viruses, IBDs, that have been identified in different countries. And I can only fit in that slide the ones that could fit, but there's many more that are constantly being identified in different parts of the world. So, what is important for you, whoever works in the field? If you work in the lab, very interesting information to learn about all these molecular aspects and antigenic variability, etc. But if you work in the field, what is the type of information that's important to you? Number one, I want to know what kind of viruses circulate in my operation. I need to know what genogroup and what genotype tend to circulate, and that's important for epidemiological purposes, because if my company has, for example, 80 broiler farms, and I sample many of them, and I find primarily one reassortant virus, then I know more easily what strategy I can use to address my problems. But if I have many different types of viruses circulating in many different farms, it's very difficult for me to answer, for example, one of the questions that was asked yesterday. What is the best vaccination program? Well, what do you have circulating in your company, or in the field, or in your country? So it's very important to do the epidemiological work, so that piece of information is important for clinicians. The other thing that I need to know is, what is the pathotype? Is it likely to be behaving like a classical strain? And if it is like a classical strain, is it like VD-IBD, causing extreme mortality, severe immunosuppression, or is it just causing immunosuppression without necessarily causing mortality? So those two problems should be addressed in a slightly different manner in the field. And of course, I need to know whether I have any of these new reassortant viruses in my operation. So, what can we do in the field to do surveillance? It is a mistake to just go out in the field, look for bursal lesions and say, well, look, I have bursal atrophy, or I have hemorrhage in the burses of my birds, without doing complementary work. You need to know in at least several of your farms, when does the bursal atrophy occur? Does it associate with evidence of inflammation, hemorrhage, edema, severe bursal atrophy, mortality, or not? And at what age does it start? And do I have any kind of recovery after a number of days? And I will show you a graph that will illustrate this better. So the first thing to do is always, what is my economic performance? Your companies don't sell bursas. You sell chicken meat, you sell eggs. So sometimes it's valid to be concerned about looking at small bursas. But if the bursas are small and your livability, your feed conversion, your average daily gain, your condemnations, your mortality during constipation, all these economic indicators seem to be within standard, then you should not be as concerned about bursal size. Bursal size is important. It's an indication, but it's not the only thing. You can do also serology. I have to be very honest with you. Many countries around the world use serology, commercialization age or processing age. I don't use it because it's very confusing. I cannot conclude many things when I look at a tiger in a broiler flock that is 35 or 40 or 45 days of age. But some people claim to be able to tell, well, this flock was challenged, this flock was not challenged. But when you correlate that serology to economic performance, it doesn't correlate very well. Not like you do for other diseases. Lymphoid organ integrity. This is important. We always have to use morphometric analysis to have an idea of how much challenge we have or how good a protection we have with our vaccines that we use for preventing immunosuppression. Mayor's disease, chicken infectious anemia, and infectious bursal disease. In the case of IBD, of course, examining the bursa is very important. And you should do that at least once every quarter. Don't do that only when you're called to a farm to look at a sick flock, because you're going to see small bursas, obviously, from IBD or from influenza or from stress or some other reason. But it's important to do a survey on random flocks to get an idea of what bursal size or what type of bursal integrity is normal for your company. And you can use bursometers, you can use histopathology, you can do bursa to body weight ratios, for example. Whatever you use, you just have to be consistent, record it, analyze it, and use it as a baseline for your company. So that's very important to do that periodically. Most companies probably should do it at least twice a year, ideally once every quarter. So 4 times a year in different broiler flocks, and that'll give you an idea of how well you are protecting. And then finally, if you do find evidence of bursal damage, take samples and send them to the lab. And ask from the lab specifically, what are you looking for? Are you looking for a nucleotide sequence? Are you looking for an amino acid sequence? Or are you looking for sequencing of both segment A and B? So first formulate the question and ask the lab to do what is useful for you. Because if you don't specify that, the lab is going to sequence the hypervariable region. It's going to tell you, well, you've got genogroup 1. Oh, okay, that's fine. Now we need another hand. I only have 2 hands. Okay. All right. So what options do we have for prevention or immunization or protection of birds? Well, the first thing that I have available, I have to think about my breeders. One of the best approaches is to hyper-immunize the breeders. What does it mean to hyper-immunize? To vaccinate multiple times with live vaccines, 2 or 3 times if you can, and use at least 2-kill vaccines. And of the vaccines that you use, if you have access to different types of strains or different types of substrate used for that vaccine, what do I mean by substrate? Some kill vaccines are produced in embryos, some kill vaccines are produced in cell culture, some kill vaccines are produced in bursal tissue. if you have access to different types of vaccines for the kill vaccination program, that's even better. But hyper-immunize the breeders. In the case of broilers and commercial layer pullets, you have the possibility of using recombinant vaccines. We saw yesterday that they are very, very adequate for use in broiler chickens and commercial layer pullets. I can't tell you that using recombinant vaccines for breeders is your only option or is absolutely necessary. It helps, but in breeders, long-lived breeders, you have different options that are probably a little bit more flexible than what you have for broilers and layers. You can also use immune complex vaccines, live attenuated vaccines, and these are experimental. These are only experimental vaccines. So recombinant, immune complex, or live attenuated vaccines. I just found an opportunity for business in Egypt. Batteries. Batteries that work. Okay, we saw yesterday this diagram, and I'm just going to remind you that whatever vaccination program you use, think about always about the complete program. Breeders, hatchery, broilers, cellular immunity, humoral immunity. How can I achieve that? Vaccinate your breeders, hyper-immunize them, protect the progeny the best you can, and then look for a way in your progeny to stimulate Th1 responses, cellular, and Th2 responses, humoral immunity. Okay, so now let's look at this very important graph. This graph was prepared based on many broiler flocks, where we collected samples from day of age all the way to 42, 43 days of age. I'm not recommending that you do that span of ages. This is only to demonstrate the following concept. And then these samples of bursas that were collected in random flocks just to see what the behavior of IBD is in the field. Then we did histopathology, and where you see a score of 1, the bursa is normal. Where you see a score of 4, there is significant bursal damage. Okay? And you can see that as the age progresses and maternal immunity declines, you start getting more and more damage to the bursa fabricius, whether the flock is healthy or not. And then, towards a certain age, there's a partial recovery. That's when we get those large follicles that are evidence of bursal tissue recovery. Okay, so in any company around the world, you would have a similar, maybe not identical, but a similar behavior. You start with infant bursas, maternal immunity declines, about 18 to 21, 24 days, you start getting significant bursal damage. It lasts about 8 to 12 days, and then you get some bursal recovery. Okay? Now, this doesn't mean that these flocks are immunosuppressed to a significant level, but it helps us to understand how our vaccination programs are working. Okay, and I'll explain that a little bit more later on. But when do you vaccinate for respiratory disease? You vaccinate primarily within the first 2 weeks. So you don't want to have significant bursal damage in your flocks. You have maybe a couple of examples of early challenge. These flocks are not going to respond well to respiratory vaccinations. And if there's a challenge with H9, H5, H7, Newcastle disease, bronchitis, metapneumovirus, they are not going to respond well. So what I want to do is delay as much as possible this damage. I want to reduce it as much as possible so that I don't have significant consequences. And if I have some bursal damage late in the life of my flock, it's probably not going to be of much consequence, not as if you have early challenge in the first couple of weeks of age. So that has to be my mindset. How do I delay it? How do I reduce it so that I don't have interference? Here's 4 important objectives that everybody should have. Number one, how can I protect early high maternal antibody and as diverse as possible by using different kinds of strains or vaccines? Number two, delay infection. How do I delay infection? Increase your antibodies as much as possible, and diversify them as much as possible if you have access to different kinds of vaccines. Number three, immunize your progeny, meaning the broilers or the commercial airplanes, without causing significant damage. We know that live attenuated vaccines have to replicate. They usually don't cause significant problems, but they will replicate in the birth nest, so they will cause at least a little bit of damage. So I'm going to select vaccines or a vaccination program that will help me protect my birds, but my goal has to be also not to cause too much damage to the birds. And lastly, number four, minimize bursal damage and achieve functional recovery, which means that even if I have some level of bursal damage from field viruses or vaccine viruses, as long as you have at least some partial recovery, that's an indication that the program is working relatively well. So, use an application of live vaccines. Live vaccine, how are we doing with time? I didn't check.
We still have time.
Okay. Advantages of live vaccines. Well, live vaccines will achieve rapid, solid immunity. It's a good primer for inactivated vaccines that applies to broiler breeders. They're easy to apply. You can inject them, you can spray them, you can give them in drinking water. They may be given at different ages, and generally they cause mild bursal lymphocytic depletion. Normally they don't cause significant damage, but they will cause more damage than, for example, a recombinant vaccine. So what are the disadvantages of live vaccines? Well, immune pressure-induced mutation. One example is reassortment of what can happen when we use more and more live attenuated vaccines. We are feeding the system with the possibility of creating more reassorted viruses. So if you use less, you use more recombinant vaccines, then you reduce that chance. Personal damage, some of them will do that, but especially the very hot ones or very invasive ones, sometimes you have to use them, you don't have a choice, but for the most part, you should not have to use those. Vaccination timing. We know very well that there is significant interference by maternal antibodies, especially when you have high maternal antibodies. But in a population of chickens, you never have 100% of progeny at day of age with very high titers all over. There's always a subpopulation that can benefit from early vaccination as well. I mentioned about the possibility of reassortment. Multiple breeder flocks contributing to broiler flocks. In this part of the world, the European Union, perhaps Central Asia, and some places in Latin America, people use the Devonshire formula very, very actively. We in North America, we can't use that because you can have as many as 10 or 12 breeder flocks contributing to one farm of broilers. So how in the world do I decide what exactly is the adequate time or precise time of vaccination? Is it 12 days? Is it 14? Is it 17 days? It's not practical for us to do that. I'm not saying it's not a good system. If you have a small farm like they have in Europe, fantastic, because you can supply that farm with one breeder flock or two breeder flocks. But if you have up to 4 million birds, broilers in one farm, it's impossible for us to really figure out exactly what is the optimal age for vaccination. So if you can use it, fantastic. If not, you have to be a little bit more practical. And then finally, insufficient control of field variables. If I have to vaccinate in the field, sometimes I don't have good control of the people that are going to apply the vaccine. Sometimes I don't even know how clean the water lines are. I don't know if the birds have been properly water starved for enough time for them to be thirsty and consume the vaccine within 45, 60 minutes, and so on and so forth. So variables in the field are important. I showed you this graph yesterday. With live intermediate vaccines, we hope to be able to immunize birds without maternal interference and before field viruses actually challenge our birds. So it's a very, very fine-tuned balance, and we have to be lucky. We have to apply a lot of science, but we also have to be lucky to be able to vaccinate at the proper age so that I don't have maternal interference and so that I vaccinate my birds before field challenge. So it's a lot more, a lot safer if I have a system where I can apply my vaccines beginning, not exclusively, but beginning of the hatchery. For that, again, recombinant vaccines have done a fantastic job. So keel vaccines, I don't have much to say about them. They're incredibly beneficial. They help you to rise maternal antibodies, and they help you to homogenize the levels of maternal antibodies that are being transferred to the progeny, and they are fairly protective, at least for the first 14 to 21 days. Okay, a couple of words about immune complex vaccines. A lot of people ask, well, how do they work? But basically, an immune complex vaccine is a vaccine that contains a relatively intermediate, between intermediate and intermediate plus, a relatively invasive IBD, but that it is coupled with hyperimmune serum so that it doesn't infect early on. It has to get into the bird, usually by injection, and then the virus is going to go to the spleen. In the spleen, it's going to remain in follicular dendritic cells. And as the hyperimmune serum antibodies decline with metabolism, then the virus starts slowly replicating. It can start replicating very slowly in a very modest fashion, beginning at 7 to 9 days, but most of the replication is going to happen anywhere between 24 and 30 days of age, or 24 and 30 days post-vaccination. And as the virus replicates more and more, it generates immune responses, both humoral and cellular. So it's basically the same. You inject birds with your vaccine virus that is coupled to hyperimmune serum. You can give it in oval, you can give it subcutaneously at hatch. The virus is essentially going to go to the spleen and other tissues, and it's going to be released slowly from these follicular dendritic cells, where it will stimulate cytotoxic T cells, like we discussed yesterday, and also is going to stimulate the production of neutralizing antibodies. We talked about recombinant vaccines yesterday. Basically, all recombinant vaccines, whatever brand of vaccine you can think of, will have as an insert VP2. Many of them have inserts from classical strains, and you might wonder, well, how am I going to protect the classical strain VP2 against reassortant viruses that circulate in whatever region? Surprisingly, they work, and they work very well, independently of the type of virus that circulates in the field. And there's published information to that effect, where it's been shown repeatedly that by using recombinant vaccines, you are able to protect relatively well against a number of different variant viruses in the field. So, I also showed you this yesterday, basically to remind you that HTT recombinants replicate actively within the first 2 weeks of age. They're not going to cause any bursal destruction, and they're going to generate cellular immunity first in the first 7 days, and then antibody responses. With recombinant vaccines, not only you can express VP2 from IBD, but you can also have combinations of IBD, Newcastle proteins, or IBD and ILT, and so on and so forth. I mentioned to you yesterday that live attenuated vaccines, the very first type of immune system stimulation that they do is cellular immunity. We don't measure cellular immunity, and therefore we don't realize that birds are already responding just a few days after you vaccinate them. With recombinant vaccines, you can also stimulate cellular immunity early on. We know, at least from the work that we've done with HTT and LT, kind of similar, different virus, but similar vector, we know that we can activate natural killer cells, we activate B cells, we activate cytotoxic T cells, we upregulate or stimulate the production of pro-inflammatory lymphocytes such as IL-1, IL-2, and IL-6. So there is quite a bit of activity in your recombinant vaccines early on. Now, the only tool that you might have to determine whether the birds are responding or not, you can use PCR to see what percent of the birds actually are HPV positive. You should not expect 100% because of many reasons that we can discuss later. But and you should not expect a strong detectable antibody response like you would when you vaccinate with a intermediate plus vaccine. It doesn't mean that the birds are not protected. The type of the form of immune response is a little bit different. So, what are we trying to achieve with our complete vaccination program? With the live vaccines, I'm trying to stimulate the production of antibodies, and I'm also trying to stimulate cellular immunity. What am I trying to achieve with killed vaccines? Essentially, my breeders to rise maternal immunity as much as possible and transfer the only type of antibody that is transferred significantly from parents to offspring is going to be IgG. I mentioned yesterday to you that at least in North America, 94% of brooders are vaccinated with recombinant vaccines. The same vaccines that are available in your market are used in North America. And I also mentioned to you that the vast majority of the viruses that circulate in brooders of North America are variant viruses. We use recombinant vaccines with a standard DP2, and they protect. If they didn't protect, 9 billion chickens would not be vaccinated with recombinant vaccines. So they do work very well. Layers. This is back in 2019-20. 80% of layers were vaccinated with recombinant vaccines. Today, about 95 or more percent of our layers are vaccinated with recombinants. So, common approaches, basically, in breeders, you can use one recombinant to live to kill. And layers, you can use one recombinant, and if it's needed, because you have a high challenge area, you can use one or two live attenuated vaccines, but you don't have to use any more 5 or 6 vaccinations like we used to in the past. Brooders, you can use a recombinant vaccine in the hatchery, and if you have high pressure from disease in the field, you can complement with a live attenuated IBD vaccination. So keep this image in mind. This is really very important. It doesn't matter if you're in Indonesia or in Australia or in Norway, wherever you are, the behavior is going to be very similar. So your objectives have to be very similar for controlling infectious burst disease. I'm about to finish. Now, for years, when we used only live vaccines, whether mild or intermediate plus, hot vaccines, etc., we had to be extremely careful on when we could actually overcome the barrier of maternal antibodies, depending on the type of vaccine that we were using. And based on that, we determine exactly when is the optimal age for immunization. I repeat myself one more time. We don't have to do this as much. In some cases, it might be necessary. But by using hatchery vaccinations, you can choose recombinants, you can choose immune complex, whatever you want to choose. If you can concentrate your efforts here and maybe complement a little later, if you truly have justification for that, you are likely to get relatively good results. So the question is, in my region, Middle East for example, what do I do to vaccinate against variant viruses or reassortant viruses when I don't have variant vaccines? It's impossible to develop a new vaccine to match exactly what circulates in the field every 6 months or every 12 months. But we do know that what we have as tools available today protect fairly well. So for breeders, we can use a recombinant IBD. That's kind of like a choice. It's not absolutely necessary. But you can use 2 to 3 live attenuated vaccines, standard, because you don't have available variant strains for you. And if you have access to kill vaccines, that contain standard and variant, that's even better. But if you only have access to standard, the more you vaccinate, the more you spread your spectrum of protection. For broilers at the hatchery, your option number one is to use recombinants, followed by live attenuated IBD, if it is justified again. Or your second option is to use immune complex vaccines, and followed by live intermediate, which in many cases is not as necessary, and it's a little bit controversial, but industry does it. And then in the field, well, you can use your live attenuated vaccines like you have used them for a long period of time. My personal choice is to use option number one, just simply because of the results that I see in the field. Okay, so once you have adopted or adjusted or optimized your vaccination program, how do you monitor it? How do you know that it's working? The number one thing is, and I put it at the end, but this is number one. When I started using certain modifications in my vaccination program, and I've observed them for a significant amount of time, I can't change the vaccination program every month, is my economic performance. What are the vital signs that are important to you? The owner of your companies, they don't care about person size, they don't care about antibodies, they don't care about vaccine strains or reassorted viruses. They care about economic figures. And in broilers, it's going to be average daily gain, livability, feed conversion, condemnations if the birds are processed, that kind of thing. So if your economic performance indicators seem to be doing well with a program of your choice, then you leave the program untouched. You should not be changing programs too frequently. Second thing, you can use, obviously, you should use a lifetime breeders to make sure that you do have at least a baseline that your company is used to having or should have. You can use a licensed serology in broilers and layers, but I find that a little bit controversial, even though many companies around the world use it. Health and versatile surveys. We cannot diagnose immunosuppression by looking at a small burst. We don't know if the bird is immunosuppressed, it just has a small burst. But morphometrics is an important indicator. If many of my birds have pale bone marrow, I start suspecting mycotoxins or CAV, for example. If many of my birds have small bursas or a certain age, I have hemorrhage and edema and mortality, but I can assume that I have a challenge with IBD and I need to do the complementary work in the lab. So these health and versatile surveys are very important to do, but not on a targeted manner. Just do them at random, using multiple ages in multiple flocks, periodically, random. That gives you an idea of what is the general health status of your flocks. Yes, it's important to look at problem flocks that are having high mortality and all that, but if you only look at that, then your impression of your program is going to be very negative. So, well, I don't have time to look at healthy flocks. I only look at problem flocks because we have a lot of problem flocks. And you spend most of your time looking at unhealthy flocks, then your impression is, well, my program's not working. So it's important to have both perspectives. So last but not least, it's important to mention also what do we need in the future for vaccines. We need vaccines that can be given at whatever age of your choice, but not causing any bursal damage or any significant functional damage. Sometimes you have a little bit of a reduction in size, but functionally that bursa is doing the job. So no functional bursal damage. No generation of reassorted viruses. That's something we cannot avoid. If you vaccinate with live attenuated vaccines, and there's field viruses circulating, at some point you're going to exchange genes, creating or generating new reassorted viruses. How can we reduce that? Using a little bit less live vaccines and using a little bit more recombinant vaccines. No interference by maternal antibodies. We would like to be able to use any age of vaccination of our choice without having to be too concerned about maternal antibody neutralization. Effective field virus cross-neutralization. Obviously, we would like to use one single universal vaccine to protect against everything. Now, theoretically, that's really not very realistic, but most vaccination programs, if they're done properly and well designed, they should overcome most of the challenges and problems in the field. Adequate onset and duration of immunity. If you have very early challenge, flock after flock after flock, here's how you have to think about the problem. You should probably not think that my disease challenge is overwhelming, the vaccines are not working, nothing works. What I use in the breeders and what I use in the growers. We have to think a little bit in a different way. What facilitates so much challenge? What facilitates such an early challenge in the field? Is it my production systems? Is it my cleaning and disinfection? Is it the number of days of downtime that I use? Is it that I allow trucks and crates and everything from the outside to come to my farm to gather chickens, and thereby bringing all kinds of pathogens to my farm? So we have to rethink how we do business in favor of controlling diseases a little bit better. And then finally, whatever you use, it has to stimulate Th1 cellular and Th2 humoral responses. So, in summary, IBD prolongs and enhances viral and bacterial infections. We know that IBD-V is immunosuppressive, and if you have immunosuppression, it's going to cause more bacterial problems and it's going to cause more viral problems. There's very, very, very interesting work that has been published in birds immunosuppressed by IBD-V. They shed a lot more influenza virus and for a longer period of time. Same thing for Newcastle, same thing for bronchitis. Classical variant, VVIBD, reassortment, and new Chinese variants, all of this is giving industry quite a bit of headache. There's going to be an ongoing antigenic drift. Antigenic drift means that the more reassortment, the more variants we see in the field, then it's going to be a slow drift towards slightly different antigenic relationship between these viruses. No matter what vaccination program you use, there's going to be some virus shedding, and therefore you should not expect that a vaccination program, as good as it might be, is going to sterilize the environment. What's going to sterilize the environment is cleaning, disinfection, fumigation, downtime, plus proper vaccination. Virus reassortment with live attenuated vaccine strains. Unfortunately, live attenuated vaccines are necessary, but they run the risk of being a source of genetic material for reassortment in the field. There's multiple different reassortment viruses that have been identified based on segment A and B sequencing. There's a novel dominant A3B2, A1B1, A3B1, and A2B1, at least in different countries, different parts around the world. And you can imagine that it's impossible to develop a vaccine for each one of them, and the many more that I showed you in that summary list that was very, very busy. Less VVIBD, I mentioned to you that we're seeing a lot less acute, very IBD problems in the field. We're seeing a lot more immunosuppression, but without necessarily the mortality that we used to have with VVIBD. What are the goals of vaccination? Delay and reduce infection, reduce shedding, reduce the possibility of reassortment, and avoid functional bursal damage. In addition to that, reduce interference with respiratory programs. So most of you vaccinate for respiratory disease, Newcastle and influenza and bronchitis in the first 2 weeks of age. So your program has to be designed such that it does not interfere with early vaccination or protection against respiratory viruses. Thank you very much for your attention.
Thank you.